and we're going to get started with Cameron.
All right, I'm gonna find myself too. All right, good morning, everybody. My name's Cameron Jensen. I've been working in the relativistic heavy ion group with Laura, Ellen, and Prakar over in West Wing. And I've been working on the LFH cal detector, more specifically, the ways to measure the tiles, the scintillating tiles that are going into the detector. So that's, for those who aren't familiar with that, it's these things like 4 centimeter by 4 centimeter. It's supposed to be 5 by 5, but there's some variance. Yeah, so I'll just give a little bit of a brief overview of what the detector actually is. And this is super top down. This isn't technical. More people will probably go into a bit more detail about it. But essentially, it's this giant array of scintillating tiles. There's 600,000 of them in total. They fit into these little modules here. And then essentially, we have radiation coming off of the collision. It strikes the tiles. They release light because they're scintillating. And then we can pick that up using a silicon photomultiplier. And then that data can get processed. And from that, we can back out all kinds of information about the type of particle, the momentum, all of that, which we then use to figure out everything that the detector is figuring out. So the origin of the problem that I've been sort of working on here is that because there's so many of these tiles and because they have to be packed so tightly, it ends up causing a big sort of problem of scale with making sure that they're all uniform, right? They pack into these little modules here, these giant, it's like 1.5 meters long or something like that, I think. And so if any of them are off dimensionally even a little bit, they won't fit. And so obviously that's an issue. But then aside from just the dimensions, they have to be exactly uniform in their scintillating behavior as well, because we're relying on that consistency in order to get good data. So that all boils down to really 2 major motivations behind my project, which is that 100,000 is a big number. That's how many machine tiles it takes in the machine. And then hands and eyes are sort of imprecise tools, especially at this kind of scale. So this is the actual box that we've been doing the measuring with. I'll run through the anatomy really quickly, but pretty much the way that this works is that it's a translational stage. You pick up a tile from the input bin, it holds it over a camera, camera takes a picture. You can get pretty precise measurements of the dimensions just by counting pixels more or less. And then it moves it back into an output bin. And then this can just repeat automatically for as many tiles as the thing can hold. So that's the translational stage there. There's actually 3 translational stages. It's that one. So you get the X, Y, and Z directions. This is the input bin. It's the white one in that photo. The output bin, that's the suction arm. That's how we actually grab the tiles. It's sort of important to not touch them with anything rigid because they're very delicate. And so we have a little suction cup that comes down and grabs them that way. That's the air supply for the suction, which we can turn on and off in the code, which is super important to be able to pick them up and drop them. That's the camera, probably the most important part of the whole thing. That's where the actual measurements are coming from. Photo background. This is just, it's a black piece of plastic. It's just there to make sure that the photos are all consistent with each other so that we can get good measurements. And then you can't really see it in this photo, but that's the UV light source. The reason we're using the UV is that it's consistent. We can close this box, make it perfectly dark on the inside, and then the UV light causes the tiles to glow this dark blue color. And so that ends up producing pictures where you have this perfect little blue square on a black background. And that is what we're actually measuring, not a regular image of the tile. And there's a photo of that later on as well. I'll point it out if I remember. But there are some issues with this design as it was. This was how it looked when I first came here this summer. Firstly, the frame beams are sort of disorganized. They were not all level with each other, a bit crooked here and there, sticking out on the edges. They were sharp as well. And so we wanted to get that sort of cleaned up. The entire frame, and by the frame, I mean the piece that the translational stage was sitting on, was just resting against the floor. It was only connected to one part on the back of the box. And so that caused both the camera and the actual stage to be sitting at a slant, which was, fine for June, but it's July, so we had to make it straight. But thank you for the people that got it. Anyway. Yeah, so that was an issue. And then The photo background also wasn't flat, which wasn't the biggest deal because it's supposed to be solid black, but we just wanted to make sure that all the pictures were consistent. And then the biggest thing is that the input bin and the output bin could only hold 20 tiles at a time. And 100,000 machine tiles doing these 20 at a time is not efficient. So most of my time, at least in this project, was spent trying to solve that. And the way that we did that was to just make a new bin. So this was the first design iteration. This was actually not my design. This was someone before me made this, but I made a few adjustments to the dimensions and printed it out. And this is more or less the same thing as we had before, except there's 8 of them. So instead of running 20, you could run 160, which is quite a bit better. And I also made this little paddle, the yellow thing there. And that was just to slot into these spaces here so that you could lift up the stack and sort of load or unload them one at a time. And this was, we never tested this inside the box. It, in theory, would have been better than the system before, but there were a lot of issues that we ran into pretty much immediately here, mostly just that these had to be loaded one at a time still. And also, you have to load them in the box because this whole thing was anchored onto the frame of the, not the translational stage, but inside the box. And so, like I mentioned, like these tiles are delicate, right? You can't manhandle them, you can't grab them with calipers or other machinery. So we wanted a way to load them safer than this while also having that capacity. And so this was sort of the eureka moment that led to this design, which was the second run through. And this is where I figured out that we can just have the part that the tiles are loaded into, which is the red thing there on the right, and the actual acceptor be 2 different pieces. And so this is anchored into the box, and that is a free floating piece. And so we can take that, it just sits on the table at an angle, then you can load the tiles in either by stack or one at a time on the table outside of the box. And that whole thing can just get picked up and slid into this bin here. So all of the loading is happening completely outside of the box. There were a couple issues with this, mostly that the handle was in the way of the camera and it was sort of big. And then also we didn't have a great way to secure it. The slot down here that was supposed to hold bottom was a little bit too tight. I had these little knobs. We were planning to just like wrap a wire around it to grab the latches on the end of that bin, but that wasn't really ideal. So then the next design was this one. This is the one that's currently being used, which same exact philosophy as before, except handles got moved, and I made 2 of them on either side so that we have 2 solid points of connection now, and also it's not in the way of the camera. And then just improved the latch mechanism, so now we can have a printed latch, which looks nicer and is a lot more secure than the wire was. There was a dream, briefly, of having a bigger one that had 5 bays in it on each side and it pulled 250 tiles, but the printer bin was too small, so we didn't go there, fortunately. So that solved the capacity issue. And then for the photo background, this was pretty straightforward. I just padded up a little model of a 6 by 6 inch piece of plastic with a little piece there that could connect to the 80/20 beam. So then that just slides on, screws in, and worked perfectly, no issues. So that's that. And then as for the frame, pretty much spent 2 or 3 days ripping all of the 80/20s out of this, pulling the translational stage out, sawing them down with a handsaw, reattaching them all, making sure it was level. And then the final result was this. This is how it currently is. So these are all straight now. There's the new bins in there. And on the right, that's an image that Nathan took that was with the door closed and UV light on. You can see them kind of glowing. And yeah, that's how it looks now. So there are a few issues. I just want to run through this super briefly. Sometimes the images don't give the best measurements, as evidenced by the meme. Space inside the dark box is a little tight. We kind of made these bins exactly to the dimensions of what the stage could go to, so there's not a whole lot of room in there. The bins don't hold the tiles exactly perfectly still because they're a little big, and static friction sometimes to pick up more than one at a time. Yeah. All right. So we also did some tests with the uniformity of the tiles for the scintillating behavior. And I'm just gonna like sprint through this because this wasn't really my purview, but I want to briefly talk about it. We put the radiation source in a box in that little holder. Beta particles hit the tiles. Oh, yep. Oh yeah, okay. Particles hit the tiles. that information goes to computer, gets processed, goes to screen. Screen goes to Nathan, who figures out what it means. Okay, so most of everything that I just talked about sort of got wrapped up in the first like month or so. And so I'm like sort of at time, but I have some pictures of some side quests. Saga. Claire isn't here, but ask her about this one. Cyclotron demo, this is for Helen and Prokar's class that they're teaching this upcoming semester. Work in progress, hopefully by the end of the summer. Trying to explain things to my friends and family. Yeah. We had a group of us, Emily, Sierra, Ryan, Isaac, Morgan. Yeah, we met with some Congress people to talk about funding and stuff. That was cool. We have another meeting. Yeah. And then balloons. So just some shout outs, mostly Prakar and Helen is my direct advisors, and then also just wanted to shout out some of the people that helped me in projects in various ways who are listed here, and also all of Wright Lab, because y'all are awesome and thank you for the summer. And with that.
Are there any questions for Cameron?
I just want you to say it because I don't say it in mine. You pointed out the UV light, but then in the updated image, we had a blue light. So why the difference?
Okay, so this is gonna blow your mind. They're both UV. So the old one. So the one that's in this picture, actually. This is a higher energy UV. I don't remember the wavelength. This is what was used before, which was a bit too ionizing. I guess Grant's eyes got hurt at some point. So then we switched to the black light, which is also UV, but it's just a bit lower energy. So it's safer and it looks cooler anyway. So, you know. Yeah, was that your question? Okay. I gotta go back to.
Oh, actually, did Ryan have a question online?
No, sorry, that was just a little applause.
Okay, great.
Nice.
Thanks. Emily?
You said at one point you were using a handsaw on the beams.
Yeah.
Did that get them level? Like, as someone who has done a few handsaws and not done them super successfully, like, did that get you to the sort of level you needed?
Sort of. So level enough, because we were attaching the 80/20s to each other with like the angle brackets. And so it didn't have to be a perfectly flat cut, as long as it was good enough to like make contact, and then you could screw in the angle bracket enough so that it held it at the proper angle. It was good enough, which that's, yeah, sort of what we.
Fair enough.
One last question. Anyone? Seeing none, thank you.
All right.